Our last topic for electricity and magnetism is a pretty awesome phenomenon known as electromagnetic induction. We're going to start out by looking at Faraday's Law and Lenz's Law. So Michael Faraday was a scientist, lived a couple hundred years ago, and he was one of the first to figure out this link between electric fields and magnetic fields. And one of the things he saw was if he hooked up a battery and put a coil around an iron ring, and then if you close the switch here, you're going to get a current through these coils, and that's going to create a magnetic field like a solenoid. And because we have the iron ring, that magnetic field is going to be created all the way around the ring, even outside of this wire. And then what he did was he wrapped a wire over here to see if he could measure some induced voltage in this wire here. So he essentially had this hooked up to a voltmeter. And what he saw was when he closed the switch, this meter would jump, but then it would quickly settle back down to zero. And then when he opened the switch, it would jump in the other direction, and then it would settle back down to zero. So he quickly realized that it wasn't a magnetic field that would create a voltage in this wire over here, a magnetic field by itself, but it had to be a changing magnetic field. So if we look at that idea a little more, if you have a coil of wires here, if you hold a bar magnet in the coil of wires, your voltmeter will read nothing. But if you move the magnet relative to the wires, you can get this needle to jump. And it jumps in opposite directions depending on which way your bar magnet is moving. So in this case, if you're moving it up, you can get the needle to go that way. When you pull it down, you're going to get the needle to go the other way, and if you just hold it there, then the needle will hold steady. We'll talk about how to figure out which way these currents go in just a little bit, but let me show you an animation, because who doesn't love animations? So here I've got my magnet, here I've got my coil. Rather than having a voltmeter hooked up here, we're going to have a light bulb. So if I grab the magnet, if I just gently put it there, you'll notice it moved a little bit, but if the magnet is just sitting there, nothing happens. But as the magnet moves, then we get an induced voltage, which leads to an induced current, which in this case leads to lighting the light bulb. And it doesn't matter which is moving, it just needs to have relative motion. And this is the basic principle behind electric generators, where if you get coils of wires moving in the vicinity of magnets, you get electricity, or vice versa, magnets moving near coils of wires. So we just need something to move one of those two objects. So often we could use something like water, attach it to a wheel, get it spinning, and voila, we have an energy grid. Hooray for Tesla and not Edison. That guy was such a jerk. Alright, back to our presentation. I mentioned earlier that we're going to talk about how to figure out which way these currents go. And to start with, we need to define a new quantity known as the magnetic flux. We use a symbol of capital Phi with a subscript B to distinguish this from electric flux, but it's essentially defined in the same way, B dot dA instead of E dot dA. And you can think of it similarly. You can think about it as the number of magnetic field lines going through a given area. And then we have the area vector, which has a magnitude of the area of the region you're concerned with or interested in. And then the direction is perpendicular to that region. That's just by convention. So the angle, if we write this in magnitude form, you could just say it's BA times cosine of theta, where theta is this angle here between the direction of your magnetic field and the line perpendicular to the region of interest, so heading out in this direction. Now this will also give us a new unit. The magnetic field is Tesla. The area here is going to be meters squared, and we define 1 Tesla meter squared as a Weber, which is abbreviated as a WB. These aren't used all that much anymore, but in the past they were popular, like 50 years ago kind of thing. Alright, so this magnetic flux, it changes depending on the orientation as well as the strength of the magnetic field and the size of your loop. So in this case, when the loop is parallel to the lines of magnetic field, then the area vector is perpendicular. This is the direction of our area vector. So again, you have to be careful whether the problem is talking about the orientation of the loop or the orientation of the area vector, because they will be off by 90 degrees, so be careful with that. In this case, you're going to have cosine of 90, which is going to be 0, so there's no flux. And you can think about it qualitatively. There's no field lines going through the loop when it's in this orientation. Now if we rotate the loop a little bit, and then at a 45-degree angle here, 45, then we get some flux because we have some field lines going through, and we can find the magnitude of that flux if we knew the area and the magnitude of the magnetic field multiplied by cosine 45. This orientation here is going to give you the maximum flux. My area vector in this case is heading off that way. Here my area vector is heading this way, so my area vector is parallel to the magnetic field, and theta is 0, so the cosine theta just goes to 1, and we get the maximum flux is going to be the magnetic field times the area of the loop. So here's a quick example. If we want to find the flux around this loop here, we have this large wire loop, and there's just a small portion within the wire that has a constant magnetic field over that region, and the area that has the magnetic field is what we call A2. So if I wanted to find my magnetic flux going through the large loop, it's going to be BA cosine theta. Well, the current is perpendicular to the loop, or parallel to the area vector, so this guy just becomes a 1. And so we're just going to have B times A. Now the question is, which of these areas do we want? Well, we want just the area where the magnetic field is. So in this case, it's going to be BA2. And there is the flux through the large loop. Now, why do we care about flux to begin with? Well, because it is related to the induced current. So this is the EMF, what we call the induced EMF, according to this beautiful little expression that Michael Faraday figured out. So it's not a changing magnetic field exactly that created that voltage that he saw in the voltmeter, but more specifically, it's a changing magnetic flux, which can be a changing field or a changing area or a changing orientation between the two. So you can rewrite this. The negative sign we'll talk about later. It's just to remind us that this flux tends to oppose changes, so it's going to oppose the voltages that were there already. So we're going to have the change in B A cosine theta, and any of these three quantities, B, A, or theta, can change in order to change your flux. So it is the rate of change of the flux that gives you the induced EMF. Okay, and this idea of what direction is that induced EMF going to be is known as Lenz's Law. And so it says that the current produced by the induced EMF moves in a direction such that the magnetic field it produces tends to restore the changed field, or the EMF is always in a direction that opposes the original change in flux that caused it. So you can think of this as just always opposing change. So if the flux is increasing, the EMF will be created in such a way to try to decrease the flux. And if the flux is decreasing, the EMF will be created in such a way to try to increase the flux. So it will always oppose changes. We'll go through some examples where that should become clear. In this case, if we have a coil in a magnetic field, it's perpendicular to the magnetic field. We don't change the orientation at all, so the only one of those three flux quantities, B, A, and theta, that is changing is the area, if we yank on the ends of our coil here. So the area is decreasing and the flux is into the loop. So if it's decreasing into the loop, we want to sustain that flux, oppose the change, try to keep it from decreasing. So the loop itself is going to try to create more flux into the page. So in order to do that, you can use your right hand rule, curl your fingers around the loop. Well, I guess initially you'll point your thumb in the direction you want the field, so that's going to be into the page, and that will leave your fingers curling around this way. So flux was decreasing, and so it's going to try to go in the original direction of flux and keep it from decreasing. Alright, another example here. If we have it originally oriented such that the loop is perpendicular to the magnetic field here, and then we start rotating the loop, Well, when it's in this position, it's a little tricky to see what's going on. But if you think about it when it's kind of at a 45, so I'll try to kind of do a perspective where it looks smaller because it's at an angle. Well, in that case, you have less flux because there's less area perpendicular to the magnetic field. So again, flux is decreasing and it wants to try to sustain the original flux. So the current will go this way so as to give you a magnetic field going in to try to sustain the flux that was decreasing in the first place. A cool application of these induced currents are induction stovetops. So here what they do is, rather than having a heating coil just get hot, they just have loops of wires that have changing magnetic fields. It doesn't do anything to your hand, it doesn't actually get hot at all. If you put glass on there, it's not going to do much anything. But if you put metal on there, those changing magnetic fields are going to induce currents in the metal, and since there's going to be some resistance in the metal, that's going to heat it up. So it reacts very quickly, and it's kind of safe because it's not hot to other things other than metal. Granted, the metal will get hot, so you can't touch that, but pretty cool technology of applying electricity and magnetism. Here are some steps if you kind of like thinking about things methodically. I'm not going to really discuss these in detail, but you can pause them or write them down if you think those will be helpful. Moving right along to a few more examples. We want to figure out which direction the current is going to be induced in all of these loops. So we have induced EMFs, which lead to induced currents. They're always in the same direction because that's how currents and voltages work. So in this first loop here, if we're pulling it to the right, it was originally in a magnetic field, and that magnetic field is going away, so the flux is decreasing once again. We've only had decreasing flux so far. So it's going to try to sustain that flux. Now in this case, the flux is coming out of the page, so it's going to try to create a magnetic field out of the page, which means you'll point your thumb at yourself and your fingers will curl in the counterclockwise direction for that one. If you want to pause it and quiz yourself first and then see how you do, it's kind of a more effective way to learn, but I'm not there to force you, so whatever. Alright, in this case we are going to shrink the loop. How we do that, that's not important. It's a shrinky dink or something. But either way, the area is going to be changing, and since the area is decreasing, the flux is decreasing once again. But now the flux is into the page, so if it's decreasing, the loop is going to try to create more flux into the page. So point your finger into the page, and this time you'll get an induced current clockwise around that loop. Okay, here we have a south magnetic pole moving from below up toward the loop. First thing we need to think about is what is the direction of the magnetic field from a south pole. Well, they go from north to south. So on the south end, you're going to get kind of these big loops doing things like this. On the south end, it will be coming toward you. This magnetic field here is a lot stronger than this magnetic field out here, so we kind of ignore the one out there and just say, okay, the south end is coming toward me. That means it's a magnetic field into the page, and it was originally not there. So this is our first case where the flux is increasing, and the loop is going to try to oppose that increase. So rather than creating flux into the page, it's going to create flux out of the page to try to cancel it. So you'd point your thumb at yourself, your fingers will curl this way, and this one will be counterclockwise. Here we've got the north pole of the magnet, so just like what we were showing here. Essentially you've got a field coming this way, and we're going to ignore the fringing effects. We're just going to say it's pointing straight that way. And in that case, there are no field lines going through the loop, so there will be no induced current in this case. Alright, here's a rotating one. We kind of already looked at this, but now our magnetic field is originally parallel to the loop. So we start out with zero flux. As this thing starts to rotate, it's increasing in flux, so it will want to oppose that increase. So as it just starts to rotate from that perspective, there's going to be flux going increasing to the left, so it's going to try to create flux to the right. In order to do that, you point your thumb to the right and your fingers will coil this way around the loop. So once again we get counterclockwise. So this is known as Lenz's Law, is just the way to figure out the direction. The idea that you get an induced EMF equal to change in flux, rate of change of flux. That is Faraday's Law. And by the way, this is just for a single loop. So if you have multiple loops, you would multiply this sucker by n just to get the overall induced current. Alright, on to some calculations.